-1. All right, hi. Welcome back to 234. I'm still your host, Steve Dragoo. We're going to talk about tangent planes and linear approximations today. That's today's topic. So chapter 14, section 4, if you're following along in the textbook or any other spot where we've written down the section numbers. And what is it that we're going to do? We're going to look at tangent planes. So we want to build this idea up from tangent lines out of Calc 1. Right? First thing we did when we started looking at derivatives was to look at a tangent line, because we said that the derivative is going to have the slope of a tangent line. In Calc 3, since we're doing multivariable functions, these things don't have tangent lines, but instead have tangent planes. But it's the same idea. The tangent plane is going to have the same slope as the function at whatever point it's at. Tangent planes, of course, notably don't exactly have slopes. Instead, what they have are normal vectors. And we'll see in a few sections that these tangent planes are really going to be constructed from the same normal vector as a function or a surface that's somewhere in space. But we're still going to have that same idea of the tangent plane being very closely related to the derivative of a function at a point. And since we have lots of derivatives, it's going to be in parts equal to the partial derivatives. So its equation is listed right here. And we're going to go over a quick sketch of how we come up with that equation. But it ought to remind you quite a lot of point slope form for just lines, right? Where it's like y minus y1 is equal to m times x minus x1. We basically have that going on, except it's got to happen twice because we have two different m's. We have two different slopes, one for the x partial and one for the y partial. And in particular, if we look at how we construct this tangent plane equation from just the equation of a line, or equation of a plane, I'm probably going to make that error a few times. Our regular equation for a plane given some point in a normal vector ABC was a times x minus x naught plus e to the y minus you see the top line that's right there. If we just solve that thing so that we get the z's by themselves, we end up with that basic equation of the tangent plane where z minus z naught is equal to a times x minus x naught plus b times y minus y naught, where a and b are going to have this definition right over here. A is negative a over c, b is negative b over c, where those capital A, B, C's came from the equation of the tangent plane. Right? They are the components of the normal vector, A, B, and C. Or if we think about that another way, if we were to take one step along our tangent plane somewhere, A is going to tell us how much the x value is going to move, B tells us how much the y value would move, C tells us how much the z value would move. And if we think about the way we want to sort of construct these slopes, right? It used to be change in y over change in x, but now we're redefining our functions to be z equals, so it's really going to be change in z over change in either x or y, depending on the partial that we're doing. So for a slope, we might expect to see something like, again, change in z over change in x might be c divided by a, since c is our change in z and a is our change in x. For those capital letters there. If we're thinking the way that slope should work, we probably expect to see something like that. But instead, we get the opposite of that. Or rather, we get the opposite reciprocal of that. Where we got a over c, which was the x change over the z change. And it's negative. But if you think again back to the way that these tangent planes get defined, instead of going from a parallel vector to create a tangent plane, we use a normal vector, which is perpendicular to the plane. And here we see that our a and b, which are going to be our x and our y partials, are defined as the opposite reciprocals of the slope that we would expect, which means we're getting the perpendicular slope instead of the parallel slope, which should line up roughly with the idea that we have normal vectors instead of parallel vectors when defining planes. So all of that to just argue my way into this equation totally works. Let's use it. So through some substitution, yep, we can say some fancy stuff like what's there. We're also going to look at a linearization, but a linearization just is a tangent plane. It is it effectively exactly. We're just going to solve our tangent plane equation for z, meaning I'm going to move the z naught or the z0 term over to the other side of the equation. And I'm going to rebrand z naught as f of x naught, y naught, right? Z is just a function value. So I can plug in my x and my y values to figure out what z should be, which means if I'm centering my linear approximation, or if I'm centering my tangent plane at a specific point, and I have z as a function of x and y, I can just go figure out the z value by knowing only my x and y values. Right, since it's a function value, I only need the two independent variables, which I can then use to also collect the z value, and going from there. I included a bit from some of my old notes. Maybe it's a little bit easier to read the equation of a tangent plane when it's all out. But again, I'm trying to argue specifically here that a tangent plane and a linearization are the exact same equation. There's just a slight branding difference. But even conceptually, these two are the same thing. We're going to use a linearization to approximate a function near a point. And we're going to say that it's probably easier to get a value off of a plane than it is to get some small variation off of the function itself. And I think we'll see that in an example coming up. Yeah, pretty much right away. So one final note on these tangent planes. We do require that the partial derivatives f of fx and fy are continuous and that they exist near this point in order for f to be differentiable there. It is an element that we're going to be glossing over. But if you wanted to do some extra reading, there's some in the textbook. I'm sure Ryan talked about that in his pre-class video. Okay, enough stalling. Let's do some problems. We want to find the linear approximation of our function f at 0, 0, and we're going to use it to approximate f of 0.1, negative 0.2. That's our goal. So if we're trying to come up with a linear approximation, again, that means we're just going to find the equation of a tangent plane. And okay, good. My pen is working. Thought for a minute it wasn't going to. Right, what do we want to do here? We need a few pieces. First, we know we're going to need our derivatives. Let's just start there. A tangent plane is most closely related to the derivatives of our function. So I'll just shorthand this, call it f sub x. And that looks like it's going to be 2 over 4y plus 1. All right, if I'm taking a partial derivative with respect to x, x is the only variable I have to consider. My denominator is just going to be treated as a constant. I can then plug in my point, which is 0, 0. Be plugging in the nice point. So f of 0, 0. And it looks like I get 2 over 1, which is just 2. That almost felt too easy, so, well, someone catches an error again. Well, you know the drill, just let me know. But I'm pretty sure that's our answer. We'll also need the y partial. 1 partial is not nearly enough. So if I'm going to go get the derivative of this next thing, well, let's see. I'm going to have to bring down a negative 2x plus 3 over 4y plus 1. 4y plus 1 squared. And then the chain rule says I should also multiply by 4. Right, so I'll have a -1 power, which is why the negative comes down, and then I'll increase that by 2, or up to 2. I increase by 1 because, yeah, this is a derivative, not an integral. There we go. You decrease the power, but it's a negative power, so it goes down. There we go. I don't know why I thought that was. Anyway, let's plug in 0, 0 to our partial y derivative. If we do that, we're going to get -3 times 4 divided by 1 squared, which is -12. Feel satisfied with that answer? We should also go figure out the function value at the point. So not looking at the derivative, just come back and evaluate the function at 0, 0. Because that's going to be our z value. And it looks like at 0, 0, I just get 3 over 1, which is 3. Okay, so I've got all the elements I need to go create my linearization or my tangent plane, because I've heard it both ways. So this is going to be z equals L of x and y. It's going to be a linearization. Or rather, it's approximately equal to the linearization. No, we keep it that way. It's f that's approximately equal to this, but I digress. I am looking at my z value, which is 3, plus 2 times x minus 0, minus 12 times y minus 0. Right, since I am centered at 0, 0, the point I am plugging in to the difference in the x's and the difference in the y's is 0 and 0. So now I want to go figure out what this approximation is. Rather than having to plug 0.1 and -0.2 into the original function, I'm going to claim it's easier to approximate my answer using this tangent plane. So this is f of 0.1 -0.2 is approximately equal to the linearization of 0.1 -0.2 -0.2. There we go. Which is going to be 3 plus 2 times 0.1 minus 12 times -0.2. And then I can evaluate that. Let's start with 12 times 0.2. It'll become positive. I think that's 2.4. Plus 0.2 is 2.6. Plus 3 is going to be 5.6. Uh-oh, I hear a lot of whispering. It's usually a bad sign for me. But no one's saying anything out loud yet. I'm going to assume that that's right. All right, let's move on to this fancy definition over here, differentials. The total differentiable dz, which we're going to use later as our integration tokens. But for now, we're thinking of these things, dz, dx, and dy, is just itty bitty changes in whatever variable they're representing. So think of like when we first did integrals back in Calc 1, and we had to do the integral of f of x dx, where dx represented that little itty bitty change in the x variable. It came from taking a limit of delta x out of the Riemann sum stuff. So tiny little infinitesimal little change. So small, it's basically 0, except that we treat it like it's not 0, because it technically isn't, but more on that later. So these differentials we're going to define, or if we want to go with the total differential, dz, looks nearly identical to the way that we define tangent planes. It's going to be helpful. So dz is just going to be the x partial times dx plus the y partial times dy. And again, that should look very, very similar to our tangent plane, where our differentials are represented by the change in each of those variables. So dz is going to be analogous to z minus z naught. Same thing with dx, it's analogous to x minus x naught. And again, this will be just a good set of approximations, and we'll find that if we do use it as an approximation, it functions pretty much identically to a tangent plane or a linearization. But again, in this section, we're going to be approximating these differentials, whereas later on, they're going to be the thing that we spend to do integrals. But more on that next chapter. So let's consider the function. Z is x squared plus 3xy minus y squared, and I want to find the differential dz. So dz, going by its definition, I know I need an x partial and a y partial, so let me actually start there. Let's get an f partial x first. It is 2x plus 3y. And while I'm here, might as well also get a y partial. And it looks to me like that is 3x minus 2y. And now I'm going to go get dz. So dz, the smallest change in z is equal to 2x plus 3y times the smallest change in x plus 3x minus 2y times the smallest change in y. And we'll call that our differential dz. But again, ought to remind us quite a lot of just the equation for a tangent plane, where I've replaced change in x and change in y with dx and dy. And I suppose I've also replaced change in z with dz. That's sort of the thing that I was trying to solve for. So if that's our differential, and I am going to grab it and slide it down to the end of the problem so it's visible as I start part B. If x changes from 2 to 2.05 and y changes from 3 to 2.96, compare the values of delta z and dz. So let's do that. Starting with dz, because that's the easy one. I've already got it. dz is going to be fx and fy evaluated at the nice point. When we're doing approximations, we want to do most of our evaluations at the nice points, and then do a little bit of the less nice points, but in the smallest possible way that we can. So I'm going to evaluate fx and fy at 2, 3. That's my goal here. So if x and y are 2 and 3, then my purple quantity looks like it's going to be 4 times 9, which is 13, times the change in x, which is 0.05. Right, x is changing from 2 to 2.05, so the change in x is 0.05. And we're going to see that change is what shows up inside of these linearizations in tangent planes most of the time, right? Because that change should just be 2.05 minus 2, which works out to 0.05. We'll see the same thing when we do the y value in a second, because it's going to be negative 0.04. But first, the yellow quantity looks like it's 6 minus 6, right? 6 minus 6. Someone do let me know if I got that wrong. But I'll finish out the equation just so you can see what I would put in if I didn't just get 0 for the yellow number. But 6 minus 6 Do believe that that's 0. So I just need to multiply 13 by 0.05. I believe that gets me to 0.65. 0.65. So I've got my dz value. Now let's go calculate delta z. But first, a question from the studio audience. Hi. I am plugging in. I am plugging in 2 for x and 3 for y. Yeah, so 2 times 2 is 4, 3 times 3 is 9, and then 3 times 2 is 6. Negative 2 times 3 is negative 6. Hopefully I got the numbers right. Okay, let's go get delta z. To figure out delta z, or change in z, I just need to know my two z values. So I'm going to go first calculate z1, which, just to recall here, z was x squared plus 3x, y. Why is my handwriting so bad on this problem specifically? 3xy minus y squared. All right, so now let's go get z1, which is what I'll get when I plug in 2 and 3, f of 2, 3. So that's going to look like 2 squared, which is 4, plus 3 times 2 times 3, which is 18, I hope, minus 3 squared, which will be 9, and that comes out to 13. No relation to the 13 above. That's just crazy random happenstance. But then to get z2, I need f of 2.05, 2.96, which of course is 2.05 squared. If someone wants to pull out a calculator, I would feel very much obliged. Plus 3 times 2.05 times 2.96 minus 2.96 squared. Now, why did the 2.96 not get a parentheses at the end? I don't know. I was thinking of something else. I know it's going to be 13 point something. We're going to come in on the underside, so I bet it's 13 point, nope. 6, 4, something? Someone have a calculator and get a number here? Does it go further out than that? 4.9, brilliant. Yeah, the 0.64 was a total guess on my part. Okay, so I've got a number. I wanted to compare that, or well, no, not yet. First, I need to calculate delta z. I've already sort of done that in my head, but I should probably explain to you what I'm doing. Delta z is just the change in the z values. Z2 minus z1. So 13.6449 minus 13 to get 0.6449. And I want to compare that to the number I got for dz, which is back at the top of the screen. All right, so dz, which again was an approximation for the change in z, was 0.65. And when I actually calculated dz the long way, by getting the long way, by getting z1 and z2, and then taking their difference, I found that I was off by 0.0001. So the idea here is that as long as I'm close to my center value, calculating these two things should be basically the same, right? Delta z is approximately equal to dz. But one of those was easier to compute. which is kind of the whole point behind tangent planes and linearizations, is that it should be easier to compute this linearization. Cool. So one of the things that we might use a tangent plane for, or a linearization for, would be to do a fancy thing. I would like to calculate the error in a volume, knowing that I've got the error in the original measurements that I'm going to use to create this box. Right? So my box is supposed to measure 10 by 5 by 8, and it's correct to within a fifth of a centimeter. Each of those three measurements will be correct to within a fifth of a centimeter. So my goal is going to be to approximate the largest possible error when the volume of the box is calculated from those measurements. And so each of those measurements could create a compounding error, and I'm going to look for the largest possible error. So first, let's figure out our target volume. Our target volume is going to be 10 times 5 times 8. Which is, in this case, 400? 400 cubic centimeters? And maybe one way, without having to do any calculus, to estimate the error that's in this measurement, just set each of these errored measurements to their largest possible value. This isn't going to be like generally the trick we want to use, but it kind of might work here. Let's calculate the volume at the error. Let's call it volume sub error, and it'll be 10.2 times 5.2 times 8.2. And again, if someone had a calculator and wanted to tell me what that comes out to, that would be great. While someone's working on that, I'm going to come back and relabel my initial volume and call it V exact. Because then my error is going to be the difference between these two things. Volume at the error minus volume at the exact value. Anybody get the error volume? It'll be a 400 and something. Sweet, what is it? 928. Brilliant. So if I take the difference between that and 400, I get 34.928. That might be one way to approximate the error. Works out very nicely in this case because each of my dimensions is a linear function. I know I'm looking for the maximum error, and so the maximum error is just going to occur if all of these individual errors go to their maximum value. But that's not exactly generalizable. Hopefully you got the word I'm aiming at, because I don't think I'm going to do better than that. We'd like a process that's more broadly applicable than just set everything to its maximum error value and hope for the best. But this is like a decent target to look at. We'll compare the answer we get in a second to this number and see how well our calculus approximation does. So if I were to do it the calculus way, well, let's go define some stuff like the volume of a box. I didn't really do that yet, but it's the base times the height. Well, let's do base times width times height. Order doesn't really matter, but I don't know. I think it'll look nicer this way. So base times width times height. And I'm going to gray out some of those words to give me my three variables. Hey, now I said turn back to black. There you go. Cool. B, W, and H for base, width, and height. And I'll just claim that they go in order. The base is 10, the width is 5, the height is 8, because again, they aren't really going to matter. So this will be, maybe I should have gone length times width times height. Too late now. It's already written down. I can't erase it. So if I were to try to create a linear approximation for the volume, right, I'll say that the volume is approximately equal to a linearization on the base, the width, and the height. So a three variable linearization. That thing is going to be the volume evaluated at 10 and at 5 and at 8 plus a partial derivative of the volume with respect to the base times the actual base minus the target value, right? The base's target value is going to be 10. Plus another partial derivative of that volume, but this time taking respect to the width. Multiply that by the width minus its target value, which was 5. Plus a third partial derivative, this time at the height, or with respect to the height. And we're going to multiply that by the height minus 8, right? Its target value is 8. So that would be the linearization that we might have for this volume that we're trying to calculate. And I want to claim that this linearization is made up of two parts that are relevant to what we're discussing. First is that very first term, which is just the volume evaluated at my target values. So this would be the exact volume. Exact, or maybe I'll call it the target volume. Exact target volume. Or the volume at all of the target values, the volume at the exact values. This is the volume I expect to see. I know that that's 400 cubic centimeters because I checked it earlier. But if I'm trying to find the error, that's the term I don't care about, right? That's what I'm expecting to get. I want to know how much I'm going to miss by, basically. Which means that all of these other pieces all of these are going to make up my error terms. Those three things. First one will be the error based on the base measurement. Really should have used length. Second term be the error based on the width measurement, and then the third term would be the error based on the height measurement. Each one contributes just a little bit to the overall error of this thing. So if I'm looking to calculate the error, it's going to be each of those partials evaluated at 10, 5, 8. Let's slide it over here so I can just write it down below. Which means I should go collect some partial derivatives. Let me just go write those down. I'll have a VB, V sub B, a V sub W, and a V sub H. And recall that my equation was just base times width times height. So these partial derivatives are going to be pretty easy. WH for the first one, BH for the second, and BW for the third. Basically, every time I take a derivative or a partial derivative with respect to one of these variables, that term disappears from the function because it has a derivative of just one. So if I'm going with the partial derivative with respect to the base, and I plug in 10, 5, 8, I would get just 5 times 8, which is 40. times the error in the base measurement itself. And I know that that thing has a maximum error of 1/5 of a centimeter, or 0.2. Right, if I'm looking at this guy right here, his analog or his new value is going to be that 0.2 right there. And then I'll keep on adding some pieces in here. The error from the width is just base times height, which I think is 10 times 8, and that's 80, at least with the way that we wrote it down. And again, the maximum possible error in the width is 0.2. So whatever width I end up getting, which will have some little bit of error in it, the difference between it and 5, which is my target value, will be at most 0.2 centimeters. So I'm plugging in 0.2 for that W minus 5. And I'm going to do the same thing for the H minus 8 in a second, just in case you were getting antsy. At the height, this one is going to be the product of the last two, 10 and 5, so 50. Hey, come on. And again, multiplied by 0.2, and I might even be able to pull this one off without a calculator. If we add these all up, 170, I think, times 2 is 340 divided by 2 would be 34. So I don't know if anybody's following along with the calculator, but hopefully you got 34, and I'll add units of cubic centimeters here. So I can compare that to the other value that we thought was a good approximation for the maximum error in this volume, where we got 34.928 cubic centimeters. So I think I've probably got the right number there. So again, the first one, we again sort of naively tried to calculate our maximum error by just plugging the numbers into the equation. Because we had a nice looking equation, that ended up being a pretty decent approximation. But if we're trying to, justify why we think we've got a good error approximation, we should probably use this calculus method. So grabbing partial derivatives and using that to talk about how each individual error measurement impacts the thing at large. Because it also helped that each of these measurements were independent. We might find some later functions where these measurements are not independent, and then that first method doesn't work quite as well. So let's go with the linearization method we just did. Cool, linear approximation of multivariable functions. All right, and I think this is all right, well, I'll have some time to talk about a couple of other things right after this. So for the last regularly appointed trick in my bag, considering the surface, it's this ellipsoid. Centered at the origin, has two semi-major axes of 3 and, all right, yeah, two semi-major axes of 3 and one semi-minor axis of 1. Believe that's all correct, but that's not really what we're here for. We're just trying to find the equation of a tangent plane to that surface at the point 1/3, 2, 2. So if I were to solve this thing for z, right, I would probably multiply the whole thing by 9, move everything that isn't z to the right side, and then take a square root. But if I write down some of those pieces in order, I think I'm looking at 9 minus 9x squared minus y squared. And then I wanted a square root of that whole thing. But this is an implicit surface rather than a function, meaning that I should have a plus or minus stuck to that square root. Which isn't great because if I'm trying to find a tangent plane, I usually need a function. Technically, this surface isn't a function, but I could turn that implicit surface into a function by picking just one of my plus or minus, and then finding a tangent plane to that new function that I created that happens to overlap with the surface at the correct point. So if I take a look at the point I am given, looking right over here, I see that my z term is 2, or more specifically, more relevantly, I see that my z term is positive. So in my choice out of the plus or minus for finding z, I want the positive square root because that's the one that'll contain the point that I'm interested in looking at. If I had the same setup, but I had the point 1/3 to -2, I would have taken the negative option out of the square root instead. But we got the nice one, or the one that you'd probably accidentally stumble upon if you forgot your plus or minus. So, bully for you, bully for us, really. Let's go calculate a tangent plane. We need some stuff. We need the same stuff we always need to take over the world. Let's go find an x partial. So if we do that, what are we going to get? I need the derivative of a square root function, which is going to be 1/2 times 9 minus 9x squared minus y squared to the negative 1/2 power. And then the chain rule says I should multiply this thing by negative 9x. Then come back through and evaluate this thing at 1/3 2. 18, thank you all so much. For some really loud whispers. Well, can't go one class without one little itty bitty mistake somewhere. Yeah, that's definitely an 18x. That's what the chain rule says. Uh, and I should plug in some points and figure out what I get here. I still have a 1/2, or let's just organize these things a little bit better. In my numerator, I'll have just the 18x part. If I plug, let's just write it all out. Negative 18 times 1/3 divided by 2 times the square root of 9 minus 1 minus 4. I think I get all of that. Not as many whispers this time, so cool. If I simplify that thing, my denominator, well, let's do the numerator first. -6 divided by 2 times the square root of 4, which is another 2. So -6 over 4 is -3 over 2. If I repeat that process for the y partial, and I can see I'm already out of space. That's not great. I'll fix it later. Fix it in post. Same thing roughly. 1/2 times, this will be 9 minus 9x squared minus 9y squared to the negative 1/2. And then the chain rule this time says I should multiply by negative 2y. First try. And we'll do the same thing. Plug in a y partial. Or plug in numbers to the y partial. We're looking at 1/3 2. And I'll get this time a -4 in the numerator divided by 2 times that same square root, 9 minus 1 minus 4. So that's -4 over 4, which is -1. So my final step was to just plug all this into the equation for a tangent plane. Just put the relevant parts on screen. This should be z minus 2 is equal to negative 3/2 times x minus 1/3 minus 1 times y minus 2. And that's my tangent plane. Hi. Yeah, fair question. Uh, I do not know where I got that negative 9y² from. I think upon any sort of inspection, it's clear that should have just been a regular y². For what it's worth, when I plugged in the number, I used the correct form of the derivative. Yeah, I don't know. It's writing fast. Threw an extra 9 in there for no reason. Oh, what are you gonna do? Math is hard. I'm not very good with numbers. It's rough out there. But yeah, our tangent plane. Do believe by the end the tangent plane equation was still right. So let's go with that. All right, with a couple more minutes, what else do we want to say? We want to look for a couple of tangent planes that are something particular. In this first part, I'm looking for a point at which the tangent plane to this surface is horizontal. So if I'm sorry for people listening to this video. I just blew a hair off my screen, but I probably blew directly into the microphone. So sorry. I'm looking for a normal vector that is parallel to plus or minus 0, 0, 1. Right, hopefully you buy that argument. If I want a horizontal tangent plane, that plane should have a normal vector that points in the z direction, since that would be that's the vertical direction. And if my normal is vertical, my plane is horizontal because they're orthogonal to each other. Which means I'm looking for a couple of pieces. I want f partial x to be 0, and I want f partial y to be 0. Right, those would be my two elements. So if I come back to what those derivatives were, right, they look, well, let's just write them. I'm clean them up and write them down right here. So my x partial, I think, is going to be 9x divided by the square root of 9 minus 9x² minus 1y². I want that to be 0. And for the other one, I think that's just negative y over that same square root. 9 minus 9x² minus y² be equal to 0. And if I want some fraction to be 0, I only need to worry about their numerators. In particular, that means x and y should each be 0. And then I can bring that back to the original equation to say that 0² plus 0² plus z² over 9 should be equal to 1. So z is plus or minus 3, meaning my 2 points are 0, 0, 3, and 0, 0, negative 3. Now, if I just put this back into the context of the surface I actually had, right, bringing the surface back into view at the top of the screen. Technically, it's an ellipse, but let's just think of it as a sphere. It would be easier that way. Ignore all the numbers, makes everything easier. If I have a sphere and I'm looking for where that thing should have horizontal tangent planes, like it's probably relatively straightforward to say that those should be at the top of the sphere and the bottom of the sphere. right? I'll have two horizontal tangent planes at the top and the bottom, which are the 2 points I ended up finding. 0, 0, 3 is at the top, 0, 0, -3 is at the bottom. And if I were looking for vertical tangent planes, I would look along the rim of the circle. So stuff that's in the XY plane. I'll fill that example out later, but also I want to point out that if you look in the notes, I have a couple more examples worked out because I thought it was worthwhile, especially when you start doing the web work for this homework set. Go look in the margins of my notes. You'll find that you're probably going to be pretty pleased if you do that. But anyway, that's the end of today's lecture. Okay, bye, 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 bye.